Earth's life support systems are literally never static. Welcome to this explainer. Today we're going to ditch the dry textbook definitions and dynamically track how our water and carbon cycles shift. We're talking everything from the quick, 24-hour pulse of day and night, all the way up to the massive, sweeping changes of the seasons. Here's our roadmap. We'll zoom in on diurnal water and carbon cycles first, then pull back to look at the physical drivers of seasons, seasonal water cycles, river regimes, and finally, seasonal carbon cycles. Let's get into it.
Section 1. Diurnal water and carbon. So diurnal is really just a fancy technical term for significant environmental changes that happen strictly within a 24-hour window. Picture the Amazon rainforest right at dawn. It's cool, it's misty, but as soon as the sun rises, temperatures climb and evapotranspiration dramatically spikes. The sun acts like a giant engine, literally sucking moisture from the lush green landscape right back up into the atmosphere. And it's wild how perfectly the data maps out that daily rhythm. That intense daytime insolation heats the ground so much that it drives late afternoon convectional uplift. Basically, the warm, moist air rises rapidly, condenses, and triggers those heavy, super predictable tropical evening storms. This rapid cyclical rainfall is exactly why the golden rule in the Amazon is that you absolutely want to be indoors by 9 p.m.
Now, this exact same 24-hour clock applies to the carbon cycle too. Think of daylight as a literal switch for carbon flows. During the day, the biosphere is glowing green. Plants are actively photosynthesizing, driving a massive net flow of carbon dioxide out of the atmosphere and into the vegetation. But when night falls, that switch flips off. Plant respiration takes over, reversing the whole process and breathing CO2 right back out into the air.
But hey, don't think this is just a rainforest thing. This exact same diurnal rhythm pulses deep in our oceans too. Microscopic phytoplankton, which are essentially tiny floating plants, bloom and actively draw down carbon in the sunlight, and then fade away in the dark. It's like the entire planet takes one giant breath in and out every single day.
Okay, Section 2. Let's zoom out from the daily clock to the annual calendar and look at the physical drivers of seasons.
Ultimately, seasonal changes come down to one thing: variations in the intensity of solar radiation. As the Earth orbits the Sun, its axial tilt dictates exactly how direct the sunlight hitting any given hemisphere is. This completely changes the solar angle and day length across the year. To give you a rock-solid, quantifiable stat for your exams, peak solar input in southern England hits roughly 900 watts per square meter at solar noon in June. But fast forward to December, that solar input absolutely plummets to a mere 150 to 200 watts per square meter. That is a massive, massive drop in the energy powering our life support systems.
Moving to Section 3, let's see how that energy drop impacts seasonal water cycles. That huge swing in solar energy completely dictates our local soil budgets. When looking at the UK soil moisture budget, which is a total favorite for examiners by the way, you can see potential evapotranspiration absolutely surging in the summer months. Because of that intense summer sun, evapotranspiration can gobble up to 80% of precipitation in lowland England. That means hardly any water is actually making it into the rivers.
We can break this shifting energy into three distinct seasonal phases. First, in summer, we get soil moisture utilization, where plants frantically use up the stored soil water just to survive the heat. Second, as autumn hits and temperatures drop, evapotranspiration falls off a cliff. Rainwater starts infiltrating the soil pores again during soil moisture recharge. And finally, during our notoriously wet winters, the soil hits field capacity. It becomes totally saturated, which leads to a water surplus and a really high risk of surface runoff.
Right, Section 4. Seasonal river regimes.
Those seasonal soil water budgets perfectly explain why different global environments see such crazy shifts in their river flows. Let's take the Madura Basin in the Amazon. It's governed by the South American monsoon system. On average, over half of its entire annual rainfall violently dumps between December and March during the wet season, while July stays remarkably dry. But think about the timeline here, because there's this fascinating temporal lag. The intense tropical rainfall peaks in January. However, because it takes time for all that water to physically move through such a massive drainage basin, the actual river stream flow or discharge doesn't surge to its absolute maximum until roughly March through May. Now, totally flip the script and contrast that tropical monsoon with the extreme environment of the Arctic tundra. In the dead of winter, tundra rivers freeze completely solid. Stream flow is literally zero. The water is just locked away in cryospheric storage. But when temperatures finally rise in late spring, all that snow and ice suddenly melts. This massive, rapid flush of water transforms the landscape into a chaotic, beautiful web of braided river channels almost overnight.
Finally, Section 5. Let's explore how these exact same seasonal shifts dictate the global carbon cycle.
Here is a classic revision question, and it trips students up all the time. What exactly causes atmospheric CO2 to drop so significantly, by roughly 2 parts per million, every single summer in the Northern Hemisphere? Any guesses?
The answer is net primary productivity, or NPP. See, because the vast majority of Earth's continental land masses are packed into the Northern Hemisphere, summer triggers an absolute explosion of terrestrial foliage. Just picture massive temperate and boreal forests all bursting into bright green at once. This explosive growth causes a huge temporary vacuum, pulling CO2 out of the atmosphere and straight into the biosphere.
So, to wrap up this beautiful seasonal carbon rhythm, spring awakens the landscape and unfreezes the Arctic's active layer. Summer rapidly delivers explosive photosynthetic growth for both terrestrial forests and huge marine phytoplankton blooms. Then, as autumn rolls in, leaves drop and natural decomposition breathes that CO2 right back out into the air. Finally, the winter freeze locks much of the northern system in ice, putting the whole carbon cycle into hibernation.
What we're really seeing here is how beautifully interconnected these systems are. Whether it's the predictable daily afternoon downpour in the Amazon or the dramatic annual burst of Arctic snowmelt, these short-term changes are all linked. The water cycle dictates plant growth, which completely drives the short-term carbon cycle.
By mastering these exact mechanisms, you aren't just memorizing geography facts for an exam. You are equipping yourself to actually explain how our planet breathes and functions. But it does leave us with one really pressing question. As global temperatures continue to rise, how will these delicate, perfectly timed short-term rhythms be disrupted in the near future? Something to think about, keep exploring, and I'll catch you in the next explainer.